Hello, and welcome to today's Saratech Enablement session. My name is Andrea Hall, and I'm the Customer Relationship Manager here at Saratech, and I will be your host today. Presenting today, we have Richard Ozaki, and he is going to be talking to you about Flow EFD. Our sessions run about 30 minutes each, and they are all posted to our Saratech YouTube channel, so make sure that you check out all of our past sessions there. We meet here twice a month just to talk about new and old features within the products that you already use, as well as tips and tricks. And we actually have another CES session coming up later on in the month, so stay tuned to find out what that one will be all about. And this is an open forum, so be sure to ask any questions that you might have. You are welcome to type them right into that questions box or the chat box over to the right-hand side. I'll be keeping an eye on that. So if you have any questions or comments, just feel free to type them in during the session, and I will just interrupt Richard and let him know what your questions are. You are also welcome to save them until the end of the session if you'd like. And with that, I'm going to pass it right over to Richard.
Okay, thank you very much, Andrea. So good morning, good afternoon, everyone attending today. So today we're going to be talking a little bit about Flow EFD from Siemens PLM, which is a CFD tool embedded within Siemens NX and Siemens Solid Edge. So just a brief background on what the tool is and what it does. So Flow EFD stands for Engineering Fluid Dynamics, and it's a general purpose 3D CFD tool. And it's very much focused at non-CFD specialists, right? So traditionally, it's been quite a CFD has been quite a tricky technology and software to get to grips with. We're really trying to bring it to the masses, to the CAD engineers, to be able to perform your flow and thermal analysis directly within the CAD environment to understand how it's going to perform and then ideally optimize that. So it's very, very accurate. It reduces the overall simulation time by as much as 75%, and it's available in a few different CAD packages. Today, we're going to be talking about the NX and the Solid Edge version from Siemens. So just to give you a very brief overview, as I said, it's a general purpose tool. So you can see a few different types of applications where Flow EFD can be used, things like mixing, heat exchangers. Today we're going to be talking about electronics cooling and PCB modeling, but it can also be used for things like aerodynamics, free surface modeling, rotating equipment, even fire modeling. So anytime your design has any sort of fluid flow or heat transfer, chances are Flow EFD can be used to, again, analyze your design directly within the CAD environment. So just a quick video. So here we have flow through a valve in Flow EFD for Solid Edge. The great thing about being CAD embedded and Solid Edge embedded is that we can actually make synchronous changes to the geometry. For example, changing the outlet of this valve, for example, right? We've made a synchronous change that would historically be difficult to do, and then the CFD or the flow updates with that instantaneously, and that's really, really powerful for doing what-if analyses. Let's have another look at an example of a LED lighting application, like a street lighting fixture. The ability to actually change the heatsink design, because we're still in the Solid Edge environment, and being able to vary parameters for how that heatsink was built, means that we can try a lot of different variants and a lot of different variations on the heatsink design, while we've still got access to all those parametric CAD features, or synchronous indeed. So we can, drag fins and move things around very, very easily, and it allows you to find the optimum really quickly. And you've got an optimized product, it's going to perform better and it's going to last longer as well. So with that, let's jump straight into having a look at the software. We don't need to see my email, but so here we have Flow. This is Siemens NX. If we have a quick look at the part, the assembly here, what we have is a PCB with a bunch of components on there, and we'd like to perform some sort of thermal analysis directly within Siemens NX. So by going to File, All Applications, simulation, you'll see that Flow EFD is just another extension or a plugin inside of the Siemens NX environment. And I'm just going to start Flow EFD, and you'll see straight away that we get this black box around the geometry. Okay, this is the computational domain, which I've actually already set up on this electronics system. So over here we have the flow analysis ribbon toolbar, where we can actually apply things like boundary conditions and materials and heat sources. This is where we apply things directly onto the existing CAD geometry. But what I wanted to focus on today was some of the capabilities we have with regards to EDA Import. Okay, EDA being Electronics Design Automation, and it's broadly a catch-all term for electronics design tools. So what I'm going to do is I'm going to import an EDA file format. The formats we support is ODB++. We do have IPC 2581B, ProStep. So these are all PCB design files, but ODB++ is probably the most commonly used out there, and all layout tools will be able to export this file format. It's very, very standard. So what I'm doing is I'm just importing that file in now, and I want to talk about how we can model the PCB and the components in a little bit more detail. So the good thing about ODB++ is that it gives all of the internal construction of the PCB. As electronics devices are getting smaller and smaller and more powerful, the PCB is actually a very critical heat flow path. So you can see, for example, things like vias underneath the component. Those can be used to actually suck heat out from underneath the part and spread it within the board to try and lower the temperature of that component. So more and more layout engineers are using the PCB itself as a heat sink more than it was being used previously, as a heat sink to really pull the heat out of the component. So it's really important that the PCB is modeled in sufficient detail so as to capture the construction and the heat spreading effects. Now, if we have a look over here, there's 3 different modeling levels in Flow EFD. So we have compact, detailed, and then material map. And I'm going to be talking about these 3 different versions and the pros and cons of each. So let's have a look at compact first of all. Okay, so let me just close this and have a look at the compact PCB. This is the lowest mesh count version of a PCB. What it will do is it will take the percentage coverage of copper on each layer, and it will create a material that represents the PCB, basically just doing a copper average within the board itself, right? So if I zoom in, this is just a single NX part. There's no internal construction there. There is a single material called what's this? If I just pull this out a little bit, board DX top level compact PCB material. And if I have a look at the properties of that, it's going to have created an orthotropic conductivity material, again, based on that copper balance. So if we go to the item properties, we can see in the axial direction, we can see the thermal conductivity. So we're looking at about 1.3. And then in the radial or in plane, again, down at the more common operating values, about 15.6. Okay, so what that's saying is it spreads a lot more in the X and the Y direction, and it's a lot more resistive in the Z direction through the PCB. And that's the most simplest representation of the board. It really doesn't take into account any of the internal copper structure. It's just a weighted volume average. And if we have a look at the summary, this whole PCB is captured with only 56,000 grid cells. That's very, very low for a thermal analysis on a board. And so it runs very, very quickly. So we can kind of get a feel for what the temperature is going to be. If I just max that out, you can see about 111 degrees C. That's kind of the temperature. And I wouldn't think this would be accurate enough to, it'll be fine if you're just trying to get the correct wattage in the system, but if you're really looking at the board in isolation, I don't think this is accurate enough modeling of the PCB to give you good results. So that's how we can model compact PCBs. The next model up from that is using something called explicit PCB. So this is kind of a hybrid method between the compact and explicit copper definition. So first of all, let's zoom in to the copper layers here. So you can, if we look at the cross section on the board, you can see there is the individual layers of the PCB are modeled, right? So you've got the thickness and the spacing of the layers. That's all correct. And if we look at the material properties, you'll see that we've got the correct materials, again, using a averaging approach for each of those layers and the dielectric as well. To augment that, we also have what we call a thermal territory under my main CPU component. Now, if I spin that around, what's actually been created here is, let me just hide the board. Okay, what's actually been created here is a region, a 3D region underneath the CPU where all of the copper is actually being created in 3D explicitly, right? So if I zoom in, you can see the vias, you can see the traces, you can see all of the detail and the copper, tracing in the vias underneath that part that's been modeled in absolute detail. So although this gives you much better resolution, it's impractical to model the whole board like this because the amount of mesh required to capture this sort of detail is very high. So for example, if we go into the results summary again, this time, look, we're up at 423,000 grid cells. So it's about an order of magnitude more to capture that section, right? And that's going to be, an order of magnitude longer to actually solve, right? So, but if we were to actually look at the temperature on there, right? So now it hasn't actually changed that much. So 113 degrees C, so the temperature's gone up very slightly, but you can see underneath there, there's hot spots where the heat is going down and traveling through the copper preferentially, and that's because those traces are being modeled explicitly, and you would not see that in the prior copper compact PCB modeling. And let's just have a quick look at the mesh as well, just to show you that we have actually resolved all of those copper regions. So you can see if I zoom in, we've got much finer grid cells around that explicit copper geometry, and that's being represented here. And we can see that. So much more grid required to model that. The third option, let's have a look at that, is something called the Smart PCB. And this is new in the latest version of Flow EFD. And this is kind of a hybrid model. Before I explain what's happening here, let's have a quick look at the results summary to look at the mesh count. So look, we're back down to 56,000 grid cells, the same as the first model, okay, the compact PCB. But instead of actually creating geometry to resolve the copper within the PCB, we're using this Smart PCB method. Let me show you what that looks like. So if I go into the edit definition of this PCB, what it's doing is it's creating an internal thermal node structure to represent the conduction paths within this solid. Okay, so if I click, let's go from averaging to fine, and if I click show, you can see I'm plotting thermal conductivity. 400 is copper, 0.3 is FR4. Very different. So even a small amount of copper has a big effect on the results. But if I zoom in, you can see that it's actually modeling those copper regions as a thermal node network. And this is if I zoom in really far, you can see kind of the pixelated representation here. But this is modeling the internal structure in absolute detail with a very low mesh overhead. Now, it does take longer to solve than the compact model, but it's somewhere in between the compact and the explicit, right? So this is kind of the best of both worlds. Now, at the moment, this is modeled as fine. I can use a averaging approach, which is actually what I've done for this particular model. And what that does is it will actually pixelate that image slightly and create a range of thermal conductivities within the board, right? So before we just had yellow and green, now we have a gradient of colors, and again, we're reducing the solve time here and being able to create this sort of even lower than faster solve time than the fine approach by using this averaging approach. And it's up to you. You can change the coarseness of the pixelation. Okay, if I it's just going to show that now. But you can choose how many pixels subdivisions will be breaking down the long side of the PCB, and that's up to you to perform that. So if we click cancel and have a quick look at the results, okay, I can actually hide that. Hide, okay. Ah, that's weird, it's still plotting on my screen. But if I create a surface plot, we'll just have a look at the temperature on the PCB. So let's choose this whole thing and create temperature of solid. It's jumped over to my other model here. Apologies, it's just showing the PCB. I forgot to click the hide button, but you can see, look, the temperature's jumped up a little bit more. It's up at 114 degrees C now, 114 maximum temperature on the PCB. So that kind of gives you an idea, and you can see there's a little bit of, I think it's still a little bit coarse on the mesh there, but as you increase the fidelity, the results get finer. So this is the NX version. What I want to do is jump over to the solid edge variety. So this is solid edge now, not NX. Exactly the same operation. We have the EDA import capability and all those different PCB modeling levels. But this time I've placed that PCB with a heatsink and a fan within an enclosure. So let's have a look at our Flow EFD setup. And you can see I have my smart PCB again. I can click show. You can see the pixelated representation of the board that I've modeled internally there. I can hide that, okay? But now we can apply things like the aluminum for the heatsink, the thermal tape. And another nice thing I should just highlight is that when you import a PCB from the Flow EDA bridge, it will actually set up everything for you: materials, heat loads, two resistor components if you have any on your board, the surface emissivities on the components along with the smart PCB. Now, when you put that PCB in a higher level assembly, you can actually choose to import from components. Right, so a sub-assembly, it will read the Flow EFD setup information from a sub-assembly and apply that in a higher level assembly. Now that's really, really powerful when you've got multiple of the same board, for example. You just need to import that board once and then apply all of those boundary conditions as from the sub-assembly components. And the way we do that is to go to Tools and Add from Components here. Okay. So now we have my board with the various cooling strategies around those parts. I can have a look at things like the usual temperature plots. Okay, I can probe this. I can see my ambience at 95 Fahrenheit, around my components up at 212, and all the air in between the gaps as well. We can have a look at cut plots. We can have a look at the cutting through the heatsink there, and I can pull this down through the PCB as well, and I can get all my component temperatures also. So quite useful. And bringing back the geometry, I can show the PCB temperature now, and you can see 215. Let me just change the units back to degrees C. So whereas before we were up at about 114, 114. So adding the heatsink and adding the fan pulls this down to about 101, 102 degrees C. So much better operating temperatures for this. And we can have a look at the add the heatsink in there as well. The legends are slightly different there. And the other thing we can do is we can also have a look at the casing temperature. So if you're concerned with touch temperatures on the outside of your enclosure, we can see those as well, and we can probe what the temperature on the outside of the casing is going to look like as well. And the last thing is the flow. So we can actually visualize what the flow will look like and how the air goes through the system, through the slots in the side, over the heatsink, and out through the fan on the back. Now, the great thing about being CAD embedded or solid edge embedded is that we can make different family of assemblies or alternate assemblies. This is the same in NX as well. And in my instance, I've got 4 different scenarios set up with different fan positions. So if I have a quick look at my table, you can see I've got 40 through to 100 millimeters. This is basically moving my fan from left to right and seeing what the delta is going to be between those different projects. So let's look at project 3, for example. As I jump over to that, you see the fan moves. My PCB, let me just hide that away. And if we were to have a look at the results, we'll see a lower temperature. And the good thing about the CAD embedded nature of Flow EFD is we can do those comparisons really, really easily. So all I need to do is go to results up here. I can do a compare, okay, and I can set up the, let's have a look at the PCB temperature and the goal plots across my 4 different scenarios, and I can just hit that compare button here, okay, and when I do that, it will create images that represents my 4 different scenarios. So here's the first one with the fan all the way over on the left. Yeah, quite a hot temperature, 101. Here, 101 point, well, the legend stays the same, but you'll notice the CPU gets cooler still, and then starts to heat back up again towards that red. Right, so we can actually quantify. So scenario 1, my U1 components 100, moving the fan 87, 79, 82, so it's starting to rise again. So project 3 is probably the most optimum for us, and that's the same for all of the components. They're the coolest with the fan directly in front of the heatsink, which might seem like common sense. And the cover temperature is cooler as well. So overall, project number 3 is the most optimum design in this particular scenario, which is this guy. Okay, and that's the real power of doing CFD in the CAD, is you can quantify the deltas between different projects to understand changing, a parameter, how much does that move the needle? What's going to give me the biggest bang for my buck? You can understand how sensitive the system is to various input parameters by looking at these different scenarios, which is really easy to set up in Solid Edge or NX. So just to conclude, just talking about a few of our customers. So Renault, they use Flow EFD very extensively in their LED headlight applications. So as cars are moving to LEDs, they are using large heat sinks on the rear and even fans to ensure reliable operation of their LED headlight units. Seiko Epson in Japan, they use Flow EFD for their projector design, so ensuring that the airflow through the system with fans is going in the right place and is cooling their projector units in the most efficient way possible to ensure long life. And back here in the US, DeWalt, Black & Decker, they use Flow EFD for visualizing the airflow in their hand tools, right? So there's fans in there, airflow. We can even look at things like clogging. So if you were to introduce contaminants and particles into the flow, where do they go? Where do they settle? Are they going to cause any issues with airflow? So with that, I'm going to take a few questions now. So Andrea, do we have any questions in the chat box, please?
I have not seen any questions or comments come through today, but if anyone has any, we'll be here for just another minute or so. You also have the opportunity to enter any questions or comments in a quick survey that will pop up as soon as we end this webinar. We just have a quick survey with just a couple of questions. Just let us know how we did today. And also, more importantly, let us know if you have any suggestions for future customer enablement sessions. We do take those seriously, and we would love to get your feedback on that. Just to reiterate, we will be posting the video of today's session on our Saratech YouTube channel, and we will also be sending it to you in an email. So please feel free to pass that along to your friends and colleagues. Make sure you follow us on YouTube, subscribe to our Saratech YouTube channel. That way you are aware when we post videos. We do long videos like today's, as well as short videos that have just some great tips and tricks. And like I said, don't forget to stick around for just about 30 seconds after this webinar ends. And I'm going to check our questions box one more time. And Richard, I don't see any today.
Okay, no problem. If you do have any questions, if you'd like to try the software or you'd like more of a custom demonstration, please call this number or email info@saratech.com. We'll be happy to organize that for you to show you our technology and yeah, give it a go.
Absolutely. Okay, thank you so much for your time today, Richard, and for everyone for joining. And have a wonderful day. Oh, and I did promise I would talk about the next CES session, which is coming up on June 20th. And we are going to be talking about the new features that are coming up in Solid Edge 2020. That has not been released to the public just yet, but we have had a few of our engineers that have gone through the training and saw what's coming up. So make sure you join us for that on June 20th. And thanks again, Richard, and I hope you all have a wonderful day.